This has been said. I am the Director of Science at HEI, and I have the pleasure of introducing the Jane Warren Award winners. But before I do that, I'm going to mention our HEI Fellowship. This is you've probably heard about this before if you've been at the conference. This is a 10-week summer program that is a paid internship for a change for highly qualified undergraduate students, rising seniors and juniors. They are paired with a volunteer mentor who are very, very grateful to all our volunteer mentors. And they have the opportunity to gain hands-on experience, research experience. They prepare a research proposal, they present their work, and they participate in professional development seminars. And we partner with the International Societies for Environmental Epidemiology and Exposure Science. And we're very, very grateful for our funders who are the American Chemistry Council, Burroughs Wellcome Fund, and individual donors. When we started this program several years ago, we weren't really sure how popular it was going to be or if we'd have anybody applying. We got about 50 applications in that year, and over the years, the applications have really grown. We had almost 200 applications this year, and what we'd like to see is that the number of institutions that these fellows represent has also increased greatly. So our outreach has been very successful for this program, and much credit goes to our staff that work very hard to do this outreach activity. They come from basically the sciences, but there are a few other majors that are represented, and the applicants are chosen on motivation, skills, experience, and the need for the opportunity. So this year we have 8 fellows that have been selected. They are going to be working everywhere from New York to all the way to Hawaii. So they have a lot of unique experiences that they'll hopefully enjoy and get a lot of benefit from this fellowship program. And if anybody wants to know any more about the program or how to support it, please talk to me. It's something near and dear to my heart, and certainly love this program that we started. Now, on to the Jane Warren Award winners. This award was named for Jane Warren, as it's obvious that it is. She led the HEI scientific activities from 1999 till her retirement in 2008. It is an award for early graduate students and postdocs and allows them to attend the conference. We have 3 people who are local and 3 that are located anywhere in the US. And I will introduce our first person, and it's Abhishek Anand, who's going to talk about mapping 2 decades of high-resolution fine particulate matter exposure and health impacts in Ghana using satellite measurements and machine learning. Okay.
Thank you for the introduction. I'm a postdoc at Columbia University, and I'm going to talk about mapping last 21 years of high-resolution PM2.5 exposure and health impacts in Ghana. And we are using machine learning, applying that on several data sets to create this data. So the motivation for this project came from the fact that there's a huge lack of air quality monitoring data in sub-Saharan Africa, as you can see in this map of purple air. And we have a high density of monitors in other regions, but we don't have as many in the African continent, mainly because of the high cost needed to establish these networks. And it becomes very difficult, even with these low-cost sensors or new sensors which are more user-friendly, to do a nationwide monitoring. So our idea is using different sets of remote sensing and reanalysis data sets, combining them together, and we are also adding some surface monitors, which are mostly well-calibrated low-cost sensors, and those are to validate these satellite-derived data sets. And then we are expanding the predictor features to capture the formation of PM2.5 and its dispersion after it's emitted from different sources. So overall, we are aiming at daily level PM2.5 data set at 1 kilometer resolution, and it's ingesting a lot of different sources of input parameters. So this is a summary of the workflow where we are assimilating different data to create a geospatial data set that can be used to train machine learning models, and we trained different machine learning and deep learning models to create this map of daily PM 2.5. And all of this data is openly available on Columbia Domain website, which is something you can get from this barcode. So we ended up using XG Boost model because that worked best for our case. And we see this high disparity in north and south in Ghana, where there's a high concentration of PM 2.5 because of the harmattan dust and a lot of fire events happening in the savanna. And this disparity is something which was not very apparent in the previous data sets or like 1 or 2 air quality monitoring stations. And it was interesting to look at that. And we also did some trend studies. Now, these 4 plots are, the top one is harmattan season average. The one below that is the annual mean, and then the rest of the 2 are wet season averages. And we saw that there was no significant change in PM 2.5 overall when we looked at annual trend. But then we wanted to do pixel-wise trend analysis as well. So we saw that in the northern area, you have a slight increase. But in the south, where you have most of the cities, air quality policies are more effective. We did not see as much of a change, but it was going down. So there's a disparity in exposure and also in the way things are changing. And we use this data to do adult mortalities using MRBRT method. And if you look at the decadal difference, we see that most of these mortalities, first of all, are concentrated in the cities. The one bottom right is Accra, and then in the middle, we see Kumasi and Tamale. And these are also increasing in the cities, and also there are some new hotspots emerging along the transport corridors because new settlements are there. And lastly, we also did disease-specific mortality study, and we saw that all these mortalities are increasing, and the overall mortality is dominated by heart-related conditions, which is ischemic heart disease and stroke in our case. So yeah, with that, I'd like to thank you for this opportunity, and thank you, HEI, for the award. And if you'd like to know more about this, we can stop by at my poster at booth number 1. Thank you.
Next up is Yiling Chang, who's going to talk about modeling truck attributable fine particulate matter and health risk in Little Village, Chicago, pre and post-COVID. Oh, there you are. Just advance with the green button.
Hi, everyone. This is Yiling. I'm a PhD student at U of Illinois, Chicago. Today, I'm going to talk about our work related to truck emissions, PM 2.5, and the health risks in Little Village, Chicago, before and after COVID pandemic. So I'm gonna bring everyone to the south part of Chicago. Little Village is a community located in the southwest part of Chicago. It's predominantly Latino and Spanish population with a total around 69,000. And it's also passed by a major highway, I-55. Another thing is that it serves as a major intermodal yard in the US. So what is an intermodal yard? As all of us might already experience, and probably it's our common daily life that we all purchase things online. And these packages got to us with medium and heavy duty trucks. And an intermodal yard is those areas with connecting different transportation systems, and the package stay or either passing through. So what is important? Medium and heavy duty trucks consist around 6% of the US on-road vehicles, but it produces over half of the on-road PM 2.5. Another thing is that communities near freight corridors carry disproportionate burden. And truck PM 2.5 and health impacts at neighborhood scale are really quantified. As the pandemic hits and then everyone gets so used to order things with a click, so we're interested in knowing about the change to the community, especially these kind of freight and truck heavy community, how the PM 2.5 impact and the health impact of truck emissions. So we use we integrate 3 EPA frameworks: MOVES, AirMods, and BandMap. And the good news is that the annual average daily traffic in Cook County between 2019 and 2023 went down, so as the PM2.5 emissions and PM2.5 concentration within the Little Village community. However, in terms of the spatial distribution, there is a consistent hotspots in the area near I-55, which was not surprising, but that means that truck emission did decrease, but population hotspots and inequities persisted. So how does that reduction affect the health? So these reductions within Little Village could translate into 0.6 preventable premature deaths per year for people living in Little Village above 35 years old. And this could correspond to around 5.2 million per year economic benefits. These values might look really small, but keep in mind that these are only people living in Little Village area. And it's further small for people above 65 years old. So what's next? We wanted to build a data adaptive exposure predict modeling to make this scalable truck attributable emission PM2.5 exposure modeling, combining moves and air mods, as well as the machine learning modelings. Also try to evaluate different mitigation to different environmental justice communities. Also, we wanted to expand the study to populations to a broader Chicago area, as well as expand age groups and additional health endpoints. And last but not least, I would like to thank all the institutions that support our study. And thank you. If you wanted to learn more, I have a poster session at Poster 3 and hope to see you there. Thank you.
Next up is Sam Cliff, and he's going to talk about West Oakland, California, a decade of air quality improvement since through mobile monitoring.
All right, I'm going to be talking about the community of West Oakland in California and how we've been able to quantify air quality improvements across the last decade with mobile monitoring. Now, this is a disadvantaged community in the Bay Area which has experienced historically high exposure to diesel air pollution, and that is because not only is it completely surrounded by major interstate freeways, but it also borders the Port of Oakland, including all of the marine and rail and truck traffic that is associated with that infrastructure. Now, fortunately, California is an international leader in diesel truck emissions regulation, as well as targeted local emissions mitigation through community engaged programs like AB 617. And so what we did was we repeatedly sampled every road within the community with mobile monitoring, and that was to try and map diesel air pollution at high spatial resolution. And we did this twice, a decade apart, and that is so we could try and quantify the impact of these different mitigation strategies. And what we found was some pretty remarkable reductions in exposure. What I'm showing you here are average concentration maps for two key diesel air pollution traces, so that's black carbon and NOx, and I'm showing you for both campaigns and the difference between the two, where we see a net decrease across the board, but we're looking at about a 60% reduction in exposure for both species in the densely populated residential neighborhoods. And with this level of spatial resolution, we're actually able to start probing why this is the case. And what we think we found is that the majority of these reductions are due to the statewide truck emissions regulations in California, where we see actually the biggest changes on those truck-heavy port and freeway roads. And we get a nice spatial decay as you move away from that major source. And this follows pretty massive reductions in fleet average diesel truck emission factors, which I have in orange, which again track ambient concentrations over the same time period within the community in red. But we do actually see the influence of those local AB 617 investments too, which have mostly been upgrading the diesel-powered port operating equipment, that off-road equipment. And we actually see that those roads in and around the port, an even bigger reduction than we might expect based solely on truck emissions regulations. And so, overall, I think what we have is a really nice case study which highlights the combination of statewide and local mitigation efforts. And so if you'd like to learn more, please come and check out my poster, number 4. Thanks.
Oops. Let's see. Next up is Jonah Hazelwood, who's going to talk about mapping the spatial distribution of sub-10 nanometer particles in Raleigh, North Carolina. Green button.
Okay, cool. Hey, y'all. I'm a PhD student studying atmospheric science at North Carolina State University in Raleigh. If you're not familiar with 10 nanometer particles, it can be very difficult to really gauge just how small that is. So I want you to consider a human hair, one of your hairs, is about 50 micrometers. That's the equivalent of 2 white blood cells put up next to each other of 25 micrometers each. If we were to take this same approach with 10 nanometer particles, you would need 5,000 of them lined up end to end to cover one human hair. Because of this small size, they contribute almost negligibly to EPA mass-based standards. So even though that they have well-documented health risks and also other risks to humans, they are essentially unregulated. So what we set out to do is, in Raleigh, North Carolina, we want to find out 3 simple questions. Where are these particles located? What is creating them? And how do they vary over distance? So here is a concatenation of, or a gridded average of all of our data put together on the roadways. We tackled this using an on-road mobile measurement system. And if you're familiar with Raleigh, it kind of jumps right out at you what the takeaway is here. But if not, we have our annual average daily traffic data. So it turns out that most of the nanoparticles that you see in Raleigh are related to vehicle emissions. Well, that begs the question of what's making them? Here you have a time series. The top line is going to be your total particle number, and the orange line is going to be the 2.5 to 10 nanometer fraction. These vertical slices that you see are going to show you pictures from our dashboard cameras, and this helps us to assess both the change over distance as well as the source apportionment. So here at time A, we can see that we're at very low concentrations. This is what we call an urban background, this ubiquitous concentration of sub-10 nanometer particles that just kind of exists in the city environment. Panel B, we have merged onto the highway, and you can see that there's a dump truck there that we're coming very close to, and that's right before we saw our large spike in concentration. And it's a very similar story with panel C. So what does this tell us? This, along with our other case studies, shows that high emission events are closely related to diesel vehicles being present. We can also see that more than 70% of the total particle number is this 2.5 to 10 nanometer fraction. And again, these are essentially unregulated. And we can also see that concentrations drop to a lower level, a very short distance from the interstate, which advocates for more mobile measurement and edging away from those just stationary air quality monitoring sites. Right now, we're working on testing some of these diesel engines and some fuel additives to see if that could be one of the reasons that we see this pattern. And here, I just have like concatenated all of these conclusions together. There's a link to the paper. I want to thank all of my co-authors, as well as all of the funding agencies. Thank you.
Next up is Anastasia Orlinking, and she's going to talk about development of an emissions inventory for Illinois warehouses for modeling the implementation of an indirect source rule. Anastasia. It's just the green button.
Awesome, thank you. All right, hi everyone. I'm Anna Olerking. I'm a first-year PhD student in the Climate Change Research Group at Northwestern University, and my project is to develop an emissions inventory for warehouses in the state of Illinois, as well as characterize how these emissions could change if a proposed indirect source rule in the state were to be implemented. So, as we're all aware, in major cities throughout the entire world, air pollution exposure is not equal. And this pattern is especially present in Chicago, where air pollution is concentrated on the south and west sides of the city, which is home to many communities of color. The plot on the left shows the city of Chicago's Air Quality and Health Index, color graded by percentile, and this represents not only inequitable air pollution exposure, but an increased risk of chronic disease. The communities in the darker shade of purple are more likely to face health disparities related to air quality, such as increased asthma incidence and increased cardiovascular and respiratory distress. One thing that may be a surprise to some of you is that Chicago is also the largest freight hub in North America, which means that Chicago is also a hub for warehouses and distribution centers. These are considered to be indirect sources, or facilities that don't inherently produce a lot of emissions, so they're often not regulated under the Clean Air Act, but they attract many different types of mobile emissions that create localized pollution at the site. For warehouses, these mobile sources are often medium and heavy-duty freight trucks. And in Chicago, we observe co-location between warehouses, major truck routes, and these high AQH neighborhoods. So, one way to possibly reduce some of these disparate emissions impacts are by regulating warehouses. In 2020, California did just this by implementing the indirect source rule. And in Illinois, a similar rule called the Warehouse Pollution Reduction Act, or the WPRA, is currently moving through Illinois legislature. The goal of this policy is to ameliorate disparate pollution impacts not just in Chicago, but throughout the entire state of Illinois. The main issue is there is no baseline. There's no emissions inventory to know what is actually attributed to warehouses. The goal of my project is to fix this and create that inventory and then see how it would change under this policy to see how effective it might actually be. We are doing this by looking at emissions from medium and heavy-duty freight trucks, on-site vehicles such as yard trucks, building-level fuel use, so natural gas generators and boilers, and transport refrigeration units for cold storage facilities. We are primarily focused on looking at emissions from these medium and heavy-duty freight trucks since they constitute the majority of emissions from these facilities. We are doing this by looking at telemetry or GPS data from an industry partner called Locus for a subset of 1,000 warehouses in the state. And this tells us how many vehicles are going to and from the site each day and roughly how far they're traveling. We are then combining this data with emissions factors from the EPA MOVES model, as well as the Energy Information Administration's Commercial Building Survey, and other private and public data sets and information from the California Indirect Source Rule to get an all-encompassing emissions inventory. And if you have any questions or want to learn more about my results, come check out my poster.
Next up is Cayenne Shiplek, who's going to talk about ambient air quality and health impacts of fine particulate matter from U.S. residential wood combustion. Just the green button for it.
Hi everyone, I'm Kyan. I'm an undergraduate researcher also from the CCRG at Northwestern, and my project aims to model the impacts of fine particulate matter from residential wood combustion across the contiguous United States. So what is residential wood combustion? That refers to the burning of wood in homes, usually in appliances that look like furnaces, wood stoves, and fireplaces. And we care about it because the National Emissions Inventory estimates that 28% of winter primary PM2.5 emissions come from residential wood combustion. However, it constitutes the primary source of heating in just 2% of homes in the US and a supplementary source of heating in 8% of homes. So in this study, I am aiming to answer 3 questions. Where does that pollution go? What are the total impacts, and who is most impacted? So to start with the modeling, we need to start from emissions. So we take emissions from the National Emissions Inventory, and we distribute that using the smoke emissions processing model to get hourly speciated emissions at a 4-kilometer resolution across CONUS. And we do that, and we feed that into the two-way coupled Worth-CMAQ model. And we do that for a baseline case, including all emissions from all sectors, and a sensitivity case, removing all the emissions we estimate to come from residential wood burning. And as a result, we compare the modeled concentrations to estimate how much comes from residential wood burning. And this is what we see. Now, a common misconception we had going into this project is that wood burning primarily happens in extremely rural areas, places where people wouldn't actually bear the impacts of the pollution. And what we find is that that's really not the case. We see the highest concentrations primarily in the biggest urban centers in the country. We estimate that in the winter, about 22% of PM 2.5 exposures come from residential wood combustion, and they're highest in cities including Seattle, the LA Basin, the Colorado Front Range, the Twin Cities, and throughout the Northeast. We then take these concentrations and we use a concentration response function, and we have all-cause baseline mortality data at the census tract level, and we use that to estimate attributable mortalities. And what we estimate is that 8,600 premature deaths each year occur because of residential wood combustion, and that's just during the winter alone. We also see that the majority of these deaths happen in some of the biggest urban areas, including New York, Philadelphia, Chicago, and LA. And we also find that we can zoom in on each individual metropolitan area and show that the places where the emissions are distinct from where the concentrations end up. So for example, this is the New York City area. You can see that the emissions are concentrated primarily in the suburbs, in places like Long Island and Yonkers, but the resultant concentrations end up everywhere. And as a result, you have some of the highest attributable mortality rates happening in places that have negligible emissions. This creates an equity issue, and you can see this throughout some of the biggest cities in the US. Unfortunately, we find that if you take the 20 biggest and most populated areas in the US, people of color are associated with less emissions in 15 of those 20, but higher exposures in 18 and higher attributable mortality rates in 17 of these cities. As a result, we think that residential wood combustion could be a potentially attractive mitigation target because it contributes a little bit of heat but a lot of pollution. The exposure to that pollution is primarily in urban areas. It contributes to thousands of deaths each winter, and people of color bear a disproportionate impact. So if you're interested in learning more, here is the full study. I will be at poster number 17, and I want to thank all my co-authors.
So I want to thank our Jane Warren Award winners, and a reminder, please go see their posters. And now Dan Kraus is going to come forward and introduce the winner of the Rosenblatt Award.
Thanks. All right, one more awardee. So the Walter Rosenblatt New Investigator Award is, it was named for Walter Rosenblatt, who was chair of our research committee and then was on the HEI board of directors. And this is an award, it's a research award for new investigators. So generally, professors who are in the first 5 years of an assistant professorship or equivalent. And our latest awardee is Amelia Wesseling from Boston University. So I'll invite her to come up. And while she's on her way up, I just wanted to say I'm very soon expecting the latest batch of research proposals for the next awardees, and so I will probably be reaching out to some of you to review them. So if I do, you might have an opportunity of influencing our next batch. So this is for you.
Thank you so much.
And then that will
Advance with this?
should.
Okay. Great. Hi, everyone. Thank you so much. And I want to start by just thanking everyone at HEI for making this happen. This is a tremendous honor and opportunity for me, so thank you so much. I'm really excited to be here. So my research largely focuses on how environmental exposures influence reproductive outcomes, but most of my formal training has been kind of on the exposure side of things, so training in epidemiologic methods and in reproductive epidemiology. So I'm particularly excited about this award because it puts me here in this room with all of you who are leading experts on the exposure side of things. So I'm really excited to learn from you all over the next couple of years. All right. So I want to tell you a little bit about my project. I'm technically the 2024 winner of the Rosenblatt Award, but my award just started a couple months ago. So this is going to be all planned research and hopefully share some results next year. So our study is focused on understanding how air pollution can influence risk of postpartum or perinatal depression in the context of ongoing climate change. So postpartum depression is a really common and potentially devastating outcome for birthing people, infants, and families. And we don't know a lot about what causes it. There's some evidence in the literature that environmental exposures, like air pollution and temperature, could play a role, but the existing epidemiologic evidence is pretty limited. So we are going to address this research question using data from Pregnancy Study Online, or PRESTO, which is an ongoing web-based preconception cohort study of couples from across the US who are trying to conceive. Participants complete structured questionnaires during the preconception, prenatal, and postpartum periods. And on all questionnaires, we collect information on time-varying residential addresses that we can use to link to exposure data. So our two exposures of interest are air pollution and temperature. For air pollution, we are using fine-scale spatiotemporal models for PM2.5, NO2, and ozone that were originally developed for the multi-ethnic study of atherosclerosis. So this is working with Joel Kaufman's group at the University of Washington. And these models have been extended to cover nationwide. And then for temperature, we'll be using the PRISM gridded climate data set. Our goal is really to understand not only if air pollution and temperature are related to postpartum depression, but also when exposure is most impactful. And so we're going to look at exposures across trimesters and then also across gestational weeks to try to identify critical windows of susceptibility. And then finally, because we are interested in how air pollution and temperature operate independently, but also as a mixture, and how they interact with each other, we're going to be running some mixtures models, including Bayesian kernel machine regression. A big thank you to my mentoring team, as well as the Presto team, particularly Lauren Wise, who is the PI. And thanks to the funders, especially HEI. And I will be at poster number 19. So look forward to seeing you there. Thank you.